Everyone, how are we doing? Welcome here today. A little bit of music. Getting everything started. Let's check it out. If you're in the chat, feel free to say hi. We're going to start with something big today. Let's get MuBot awake here. Doing a bunch of things in the background, getting ready for the test. Campus content number 7. That's a great way to start the day. Savannah, thank you for being here. Let's get campus content number 7 up and going. My phone is buzzing so I can log in. Oh my gosh. Logging in. Logging. Oh, I didn't log in. It was my mom messaging me. How are you doing this morning, Savannah? Let's throw out another 100 points. So MuBot should be awake now. There's MuBot. Campus content number 7 going to start real soon here, as soon as we get logged in. Logged in. Is this you logging in? Yes, it's me. Great, doing well. Crazy week, crazy day. This has been a busy semester. Last semester we moved. That was busy. And this semester, dealing with maybe legal stuff. Ah! A lot of fun. A lot of fun in the background. But we're gonna do the review sheet after this. But yeah, dealing with ads. My wife and I are like paid for some work. Work didn't get done proper. Company does not want to do work proper. Company maybe caused damages. That's all I'll say about ongoing trying to get company to rectify. That's my life. That is the factual nature of our experience. The factual nature of it. Under our view, it was not done right. And under the view of professionals who have examined it. And that just causes a lot of work. They would just answer the phone and resolve. I've examined 20 minutes. Oh, no worries. We're gonna get started with it right now. I was clicking through, getting everything loaded up. Let me save these documents here. Hey. Okay. I'm gonna put the notes. We're gonna need a note slide, and we're gonna get started on some Canvas content here. Canvas content says we have 2 people watching, but the other person might be me. Let's write this in the notes. Canvas content number 7. And stat tool 1. Canvas content 7. Sampling distribution. Let's do this. Okay. What is p hat? So don't even, just first look at the question and think about what is p hat. Let's get the review formula sheet up here, but what is p hat? This is a great question from yesterday. We might still have the notes from yesterday. Let me see if we have those, but try to answer in the chat right now. What is p hat as we do this? Let's see if we have it. Close. It's not a population sample. It is, so population sample's kind of an oxymoron of sorts because population and sample don't go together because the population is all the data. The sample is the subset we take as our sample data. So what is p hat? N, lowercase n, is sample size. Capital N is population size. And these are the notes from yesterday. Here's the notes on p hat. What is p hat? What is p hat? This is good review right here. This is good practice. Like, these are the things we should know for the test and that make understanding it easier. It's like understanding, like if you understand what salt is, you know when to put it in dishes. If someone says just put salt and you're like, well, why? And you're like, well, it's gonna add, doesn't add acidity, does it? It's like it has a certain taste to it. You have to taste it, you have to know what p hat is. So what is p hat? This will answer our questions. Remember, we're not just trying to get it right, we're trying to understand why we're getting it right. What is p hat? You have 100 awesome friends. You have 100 awesome friends randomly sampled. Amazing grammar. You know that 30 own dogs. What is p hat? So we've got everything highlighted right here. What is p hat? And then it does say it right there. It's sample proportion. Are the conditions anywhere mentioned right here? Are the conditions for checking if it's normal mentioned at all? Are the conditions for checking if it's normal mentioned at all here? This is a self-contained slide that we wrote yesterday. Are the conditions? No, they're not. They're on the other slide where we talk about how do we know if the distribution is normal. And Savannah, good work. We're 500 points. This is the practice, and a lot of people get these wrong on the test. because the chapter has you check conditions. But here's the thing. To calculate p hat, you only need to know what two quantities. And good work right here. This is the practice. No, you're right. So they're not on this slide. And good practice. Remember, this is the practice. Like people come, sometimes people get hundreds on the test and they're like, how do you know everything? You're like, well, because I got it all out of my system. I practiced. I got it down. X and N is how we calculate p hat. There are no conditions for calculating p hat. It's just the sample proportion. So you don't have to meet conditions. You meet the conditions to check if it's normal. So the whole point of meeting the conditions for the sampling distribution of the sample proportion is to see if the distribution is normal. You don't meet the conditions to calculate p hat. You can just calculate that from x over n. All other things being equal, the larger the sample size, the smaller the standard deviation of the sampling distribution. Now this is key at the end right here. It says the smaller the standard deviation of the sampling distribution. And let's go take a look right here at this. And I might, this is due when? It might be, if it's due today, I'm going to change it. Here are the equations right here, and you can see this one specifically that we have circled. I'm going to delete the highlighting off of it so it's a little easier to see. But what happens to the standard deviation as n increases? So as n increases, what happens to the standard deviation? So we're asking, as this value n gets larger, what happens to the standard deviation? Well, the distribution does become more normal. That's two parts of the central limit theorem. The central limit theorem states that it'll become more normal. That's one of the parts. But what happens to the standard deviation? Mathematically speaking, so you have to look at the formula right there and say, as this value of n gets larger, what would happen to standard deviation mathematically? And you could write in some fake values right here, like 0.8 divided by square root of 10, or 100, or 1,000, or 10,000. So what happens to the value of this as this bottom number gets larger, which is n? And I just solved it. It decreases. Exactly same answer right there. And that is the second part of the central limit theorem, that the distribution becomes more normal and tighter. The tighter is the second part. So it's getting tighter because the standard deviation is getting smaller. And so I think that's what it said. And it does say the sampling distribution. We do add trick questions where we say the original data or the sample data. So the smaller standard deviation, yes. As sample size increases, standard deviation gets smaller. Mathematically, that is true. Now, for these questions right here, you need to do what? You know it. You love it. For 100 points, you got to say one thing in the chat. We're going to start marking it here. A lot of people do these questions way too quick, and we wrote a step-by-step condition for it yesterday. We wrote a step-by-step. We are right here. I'm going to delete a lot of this. We're just going down to the third. Notation, brother. Got to do the notation. So here's the question we did yesterday, but we're just going to input this right here into the steps. So we have a step-by-step for this. Write down these steps and know them. Here is the question itself. And the step-by-step we wrote out to solve these say, and I'll go over here to this screen. It says first we need to find P. P is the true proportion. So where's the true proportion? They take a cluster sample of 500. Oh, it's in the thing. It says it's greater than 3%. I hate that it says greater than 3%. We'll just say P is equal to 3%. The question states this. Whoops, I got this slide a little off to the side. The question states 3%, and I can show you that. It might look a little weird on the screen here. It says it right here. I wish it just said is 3%. They say is greater than 3%. I don't like that we wrote it that way. Might go ahead and change it right now, technically. Can I go ahead and change it? Let me go change this. A student brought up an issue a long time ago where they were like, what if it's 100%? Because that would be an issue. So a student mentioned that, and it should just say it is 3%. I think that's better because there's a theoretical quandary. So I'm going and finding this one right now and changing it. And there's not that many questions. We've actually done most of them. Okay, now the question says it is 3%. And I think I can show everything here. Well, you probably saw the answer too, but that's all right. So now it says it is 3%, so I prefer it to say that. And with this right here, it's stating P is 3%, then what is Q? You have to know how to find Q. Maybe, I think it would be. You can, Savannah, if you got the numbers, let me know, but I think you're right. So what is Q? So we have to find P. We've already found P, which is a proportion. What is Q? if P is 0.03, Q is equal to what? How do we find Q? Once again, think of these questions as testing your knowledge on different things. Close to Savannah, 100 points right there. 0.97. Yep. 0.97. Yep. Double checking the calculator all the time. Don't worry, I get it wrong all the time. Can we do chapter 10 homework, or has that been done? Yeah, we've done. We can do it again. Do you have chapter 10 homework still? Yeah, you can do it anytime. Yeah, which ones are you working on that? Thank you, Catherine. We have done a lot of it, but let me know which question you want to do. We can do that. So now we only have to check the smaller one. It's a compliment. Great job, Savannah. And here is N, and N is what? 7,000 or 500? Which of those is N? Which of those is N? Lowercase n. Is it 7,000 or is it 500? The company makes 7,000. Great job, Catherine. Which of those is N? Lowercase n. One of those is lowercase n. Yep, that's it, because that's their sample. That's what lowercase n is. It's sample, and this is population size. And so all we need to do is multiply this by 500, and we get is equal to 15. And then we can take 0.97 and multiply by 500, and that is equal to 485. And we just found both NP and NQ. So we'll highlight this right here. This is NP, and that's NP, and this is NQ. Technically QN, but they are both greater than, so we pass, because both of these over here on the side, we'll do it in a nice little green, are greater than, so we are good, because both are greater than 15, or 10, both are greater than 10. I'm gonna erase the work. Oh no, I did so much work, I can't erase it anymore. Well, we'll have to change the slide if we ever want to get it back. So did too much work on this slide. Is it met? It is met. So that is met. We are good on that. It is met. The conditions for a sampling distribution and sample mean when you know the true mean are what? Condition 1 is always random. Condition 2 is always 10% from chapter 13 forward. Be careful. Remember, regression has different conditions. And then the third condition is going to be the large enough condition. Now, this really comes down to memorization, and write this down. When doing the sampling distribution of the sample mean, the third condition is large enough. I have a good video we've already made going over that, but you want to go to the slides right here and write down the third condition when doing that success failure for proportions. The third conditions for doing the sampling distribution of the sample mean is going to be the large enough n condition. And you'll usually hear me say large enough n right here for large enough sample size. Check out the lectures where we go over this, and this is the third condition for the sampling distribution of the sample mean. So very important right here, this is what we're using, and these are the conditions we check, and the third condition is this right here. Food company salmon, you got it. And the last one is, the central limit theorem relates to which of the following conditions, and the reason we do the central limit theorem is to see that the data is more what? As the sample size increases, it'll become tighter, and it will become more what? The whole point of doing the central limit theorem is to have a distribution that is what? Is it to say it's a random distribution? Is it to say it's a 10% distribution? I don't even know what that means. I know what 10% condition is. Here's the central limit theorem in action. You can have a distribution that is highly skewed, and with a skewed distribution, you can take a sample of 25, and the resulting distribution of distributions, or the resulting sampling distribution of means, will be nearly normal. So it becomes more normal as n increases. And we go into more depth in this in the lecture, but the point of the central limit theorem is to know that the standard deviation will get smaller, i.e. tighter, via the formulas we just looked at for a previous problem, and also the distribution becomes more normal. And then we can use things like the empirical rule, the 68, 95, 99.7, and z-scores to talk about this distribution. We cannot use it for this distribution, which some of your MyPearson questions go over, so it is definitely checking to see if it's normal. That's the whole point, and we have that in our slides from yesterday. The whole point of doing these conditions and the central limit theorem coming into play is the conditions for normal. So if we meet the conditions, it is normal. We'll do one more version of this right here. We should have got a 10 out of 10. I didn't look, but I'll assume I did. We already did this one right here. The standard deviation gets smaller. It's true. Success failure condition states that your measurement must be binary, either a success or failure. Now that is kind of implied, or would necessitate binary data, but that's not what it says. The success failure condition states you need at least 10 successes, at least 10 failures. So look at the notes right here. You don't see me talking about binary. That's not what the condition states. It states there must be at least 10 successes, at least 10 failures. And I have people say to me, well, why does that matter? Well, if you don't have at least 10 successes and at least 10 failures, then what would happen? Well, we're checking conditions to see if it's normal. Let's say you go out and buy lottery tickets, 100 of them, and they have a 1% historic probability of success of winning. This is what the distribution would look like. It doesn't look normal. Let's say you talk to 100 random people and you know historically, or the truth is that 40% own a dog. That looks normal. It's because with 100 people, you'd expect 40 successes and 60 failures. You can figure out the expected successes and expected failures by doing NP, which is going to be 200 times 40 now, percent, which is 80 successes. 40% of 200 people are expected to own a dog, which is 80 people. That's where the peak of the distribution is at, the unimodal, symmetric, normal distribution. And then you see we get a standard deviation, and this would be accurate to use the mean and standard deviation. It actually goes back to the earliest chapters in the class that the mean and standard deviation should be used for normal data, and then we can calculate z-scores. But if we don't have a large enough, enough successes and failures, then we won't get a normal distribution. Right here, you only expect 0.4 successes, or we'll do this where you only expect 1 success. If there's only a 0.5% probability of winning on a lottery ticket and you buy 200, you only expect 1 to be a winner. Now 0 is also likely. That's so cool how the peak is right there. And we could figure these all out mathematically, and it actually goes into the chapters we've already done, because this probability right here, what is 0.995 raised to the 200th power?
It's approximately 0.3669.
So there you go. That number right there is losing on every lottery ticket out of 200. Like if you buy 200 lottery tickets and they're all losers, then you have this. So you can see how these chapters kind of overlap. We don't really use the binomial applet, but it can show you things where if you meet the success failure condition, it'll be normal, or if you don't meet it, it won't be normal. So here we would have 40 successes, and it can be modeled using a normal. And this would be a non-continuous distribution. It's a discrete distribution because remember we did continuous and discrete at the start of the class. A lottery ticket's either a winner or not a winner. You can't have a half-winning lottery ticket. So this would be a discrete distribution where the normal is continuous. It contains infinite numbers between them. So these topics of discrete, continuous are used throughout statistics for things like the binomial distribution, which can be approximated via normal, but the normal is also continuous, has numbers between all these, and the binomial is discrete, where it has only whole numbers. As you can see as I hover over these, it's only whole numbers. I really love the convergence, 100 points if anyone listened to all that, but I love the overlap of topics that we introduce you to that can help you understand things like continuous or discrete. Discrete just means whole numbers, continuous means decimal places, normal can be continuous, the binomial is discrete whole numbers. Anyways, did we do all questions in this? Let's check it out. I think we did them all. The central limit theorem relates to the nearly normal. What are the conditions? The last one is the large enough n condition, and this is false. Not saying it needs to be binary. Should have two 10 out of 10s. Two 10 out of 10s, we did it. 10 out of 10, all 10 out of 10s. Let's go do that salmon question. It's salmon time. How did people do on the quiz last night? How you doing, Catherine, today? Chapter 10 homework. Good practice on chapter 10. Good, I like to hear that. I'm doing pretty good. I'm like a stressful week, semester, I was saying. I hate it. Like, I always want to hear if someone's having a bad day, because everyone like points out, oh, people just reflexively say good. But no, a lot of times people are doing good. I'm doing a 6 or 7 out of 10. Usually I'm 8 or 9 or 10 out of 10. Today I'm a 6 out of 10, 6.5 maybe, 6.5 out of 10. I'm doing good. I'm better than average. But I got the things weighing me down on my shoulders. So that's, I agree. I'm a 6/7. I agree. We should walk up to people and don't say, how are you doing? Say, rate your day 1 to 10. Say that to people. And they'll be like, what? You'd be like, just give me the numeric information. Discrete values only, no decimal places. Say that to, they'll just be like, you are weird. Like, yes, I do stats. I am weird. I think, yeah. A lot of people just reflexively, and I reflexively say good sometimes. So, especially if I'm going through something crazy, and I'm just like, I'm good. I've seen how people did on the homework real quick last night. I was sending out reminders. I watched quiz results. I watched all those things. How many people didn't do it? Only 9 people didn't do it. I'll take, wow. Wow. Really good results. Really good results. Wow. I am very, very happy with the results of last night's homework. The average last night, I can show this if I just hover over the averages. Chapter 12, people really struggled with. And I owe people, what did I say, like 8 points on, gave points on another chapter. Let me go add the points here for chapter, the sample survey one, which is chapter 10, which people did better on than 12. I'm going to go up the grades here because I swear I said give some points to it. So let's increase the points by, how many is it? Out of 12, we'll throw on here. So I'd give, I think, like 8 points. So we're doing this really quick right here. Yeah, I need to throw a point on here. 1 point. Select students. I don't wait. Chapter 6. Oh yeah, that's why I was like, we can do it. We can do chapter 10. That's why I was confused. And I was like, the sample problem. I was like, yeah, that's the sampling distribution of the sample mean. So we'll do that right here. This, stop being weird, computer. Really? I'm trying to select all the students to give the points I said I would give. It's literally not letting me click the button. All right, it's just stalling out. Okay, let me go. Can I have 2 screens of? Okay, it's completely stalled. Well, while we wait. It did it. It did it. It just literally took that long to click all of it. Okay, there we go. We have increased it, and we're good. And now people have like. I remember saying this one's a really tough one. So now people have 108. I don't think I said give more than 8 points. And now I just have to click save because I've done it before. I didn't click save, and people don't get the points. Good morning, Jonah. We're giving some points right now. I think this is saved. Really? Given some points, and we're about to do some chapter 14. So ask those questions if you got it. This is so, I wish you could see this. It's so convoluted. There we go. Okay, we're good. Save changes, and we should see the grades increasing right there. And I can show this. Let me make sure that's off the screen. It's saved? Changes are saved. Let me know if you don't see the increase in your grade. Go to the main screen. So these were the averages. Chapter 12 destroyed people. You can see right here, no personal information, right? Good. I checked before I did it, but always that slight worry in my head. Last night, really good right here. I haven't put in the zeros for last night. I'll do that. Well, let's just do it right now. One of the bummers, as I just do a tiny bit of busy work here, is we as the instructors have to enter in the zeros. I know that's like, oh, I got to enter in the zeros, but it's still like, why doesn't it just auto do that? Why doesn't it just, after the assignment is complete? Because we've actually had issues in the past, and it's not their fault because they're like a new instructor, and there's a lot of things to keep up with, and then they don't know that. You would think, because Canvas does it, MyPearson doesn't auto enter in zeros. So I have to go in and manually say the zeros are in. So now the zeros are in, and the averages are going to change because there's 9 zeros. So you can see I'm very proud last night where we had a 96.25 median, and this would be the mean, because the mean's usually going to be lower due to the left skew of the distribution. But here's the weak point right here. Chapter 12 really got people. Chapter 12, maybe it was because it was right before like Easter break and all that stuff. It just really, I mean, we had 90s on everything till chapter 12. That's all right. It happens. Overall, still doing really well, but the 78 average shows that there is a gap in people's knowledge. So I'm really worried about the chapter 12 knowledge. We might do some on that here in a little bit. Okay, thank you, Catherine. Any other questions than the, what you call it, the salmon question? Chapter 12, homework. Okay. Here it is, the salmon question. It's a salmon. Here we go. I just do the full homework. Standardized test for graduate students, waiter, waitress. Oh yeah, yeah, totally. Yeah, so 3 others. You just want to do the whole thing? The whole thing at a moderate pace. Have I not labeled the start? Oh, I did label start. We do the full thing. I think waiter, waitress is in this one. Okay, so chapter 14. Okay, let's do this. Let's do the full thing here, Jonah. Let's get it going. Okay, so the first thing you need to do when you get to any problem is do what?
Notation.
Tell me 400 points in the chat. You know it, you love it. Leo's back. Leo gets mentioned every semester now. The first thing you need to do with any problem is do what? We do this every problem, every time. What do we do? Sweezy's ready. Good to see you, Sweezy. What do we do? Notation, brother. You got it right there. Sweezy, good to see you. I think we met out in Haslam, right? So what do you see right here? Tell me the colors. I'm going to mark them right here, and these are the different what's. So what do you see? Yeah, that was awesome, Sweezy. Yep. What are these things? What are those? What are those? What are they? So the different colors, tell me what they are. I got beat at Mario Kart. Sad day. I had a good time. I was on the leaderboard. I was like, I think I was third for a little bit, but man, the top time, I played a lot too. The mean is blue, and it is mu. So that is the true mean of quantitative data. Be careful, there are differences between mu y bar, which is the expected mean for the sampling distribution of the sample mean, mu p hat, which is the expected mean of the sampling distribution of the sample proportion, and p and mu, p is true proportion, and mu is true mean, and p hat is sample proportion, and y bar is sample mean. Those are all different quantities, so know the differences. We'll do that probably in a little bit, but that is mu because it's the true mean. And then this is standard deviation, great job right there. This is sigma, which is true standard deviation, which is not S, which is sample standard deviation. And SD, things like y bar, is the standard deviation of the sample mean, and SDP hat is the standard deviation of the sample proportion. Be very careful, that is sigma right there, which is true standard deviation. It's like, I know the salmon has an average weight of this, and I know the salmon has a variation of 2. What are the greens? What are the greens? We're almost done because it's going to ask us for the standard deviation of the mean. Notice this says the standard deviation of the mean, and this is going to be the standard deviation of the mean right there. So that phrase, standard deviation of the mean, is that, not the standard deviation, which is just sigma. Those are different, and thank you, Catherine, for asking. Don't worry if you don't know, just say you don't know, and I'll usually tell you the answer, just so as you're following along. Those, and you get 100 points right there. In green are different sample sizes. These are each n for different sample sizes. So those are different sample sizes, and if you notice, the formula for this is going to be sigma over square root of n. Once again, the formula sheet has these formulas on there. So sigma over square root of n is found on the formula sheet for the sampling distribution of the sample mean, and that's the important thing to know. If you mark the notation and you go to the formula sheet, we'll go over here to the formula sheet now. I highly suggest printing this out beside you while you're doing the work. If you go here to the formula sheet, you will see down here, right now, we see standard deviation of the mean is equal to sigma over square root of n, and we have it right there. So you have to know the formula sheet. You have to know where to look, and there it is. So with that information, we just plug in. So the first one is going to be 2 over square root of 9. The next one is going to be 2 over square root of 36. Next one's going to be 2 over square root of 81. And each of these will solve out to things like square root of 9. That's going to be 0.66 repeating. And that's going to be 6. That's going to be 0.166 repeating. And right? No, it's a third. It's a third. What am I doing? I don't know how to math in my head anymore. Do it on the calculators too. Check your work. 0.33 repeating. So that's going to be 0.33 repeating. And the last one's going to be 0.22 repeating. So 6, 3, 2. And those are the answers to the different standard deviations. So that'll round to 6, 7. Check answer. That'll round to 0.33. Notice that as the sample size gets larger, the standard deviation got water. As the sample size got larger, the standard deviation got water. So as the sample size got larger, the standard deviation got water. As the sample size got larger on the bottom there, the standard deviations we calculated got water and water. When it went from 9 to 36 to 81, the standard deviations got water. As the sample size was getting larger, as we were taking larger samples, the standard deviation of the mean got smaller. And that's one of the two things of the central limit theorem, which we've been repeating, especially in the Canvas content. Once again, we try to verge these topics into something it might not ask. The multiple choice kind of gets into this. It says which of these would be the most normal, and this is the central limit theorem. The central limit theorem states two things. As n increases, the distribution will become more normal, and it'll become more tighter. We just saw the more tighter, so which one has the largest sample? The palettes. So the palettes would be the most normal. So the palettes, because as long as the underlying, nope, the palettes, regardless of the underlying distribution, the sampling distribution, the mean approaches the normal as the sample size increases. And we have this right here in the central limit theorem, where you might have a skewed distribution. And if we go right here and take a sample of 25, this becomes a mean of 25. And when we repeat this process multiple times, we would get multiple observations of means from random samples, condition 1, and then we start to build a distribution from the multiple times we're doing this. This is just doing the process multiple times right here and showing you what would happen theoretically if we kept doing it. And now I've done it a ridiculous amount of times. And you get a normal distribution. Once again, the reason we check conditions is to see if the distribution will be what? The reason we check the conditions like random, 10%, and also large enough n is to see if the distribution will be what? The reason we check the conditions like random, 10%, and large enough n is to see the distribution will be what? Normal. Yep. So to be able to say it's normal, the distribution of the means, we have to have randomly sampled data, less than 10% of the population, and meet the large enough n condition. We've got into more detail in other videos, but that's the whole point of checking these. You do not need to check them to calculate y bar, because y bar is just the sample mean. Y bar would be the sum of the observations over, so sum of y observations over sample size equals y bar. Just add everything up and divide by n. You do not need to check conditions to find y bar. That's sometimes a question on the test. You can just calculate y bar or p hat by themselves, and we can talk more about p hat, but that's the other chapter, so I'll kind of not do that right now. I think this one's a little bit of work right here. So here, we'll even mark the questions for people. I'll be super nice. Right here and put question 1. And so this right here is 33, back to a 1, Pearson, chapter 14, question 2. A standardized test for graduate students, admissions has a mean score of 144 and a standard deviation of 7, and a unimodal symmetric distribution of scores. A test preparation organization teaches a small class of 4 students and a larger class of 36. So what's the first thing we do? And I need your help doing this. What's the first thing you do when you get to a question like this? First thing you do. You know it, you love it.
Notation, brother.
And I need your help doing it. Notation. So what is some of the notation? I'll start coloring things. You just tell me what the colors are. Be very specific. Like tell me, because if you say one thing, it could mean another thing, but be very specific. Like, think about what the formula sheet looks like. I'll go back to the formula sheet, and we have to go grab right here. Kind of, yes, you're on the right track, but tell me what exactly. I'm gonna throw you another 100 points right here. You're on the right track, but be very specific. You use the formula sheet information down here to very specifically say which one's which. I think you know it, but I just want to be very, very specific. Because mean and standard deviation can mean different things. You haven't said anything wrong, I just want you to be more specific. You haven't said anything wrong. You were very, very correct. Close, Jonah, close 100 points. It's not sample standard deviation, though. Don't worry about being wrong. We throw out points for everything. So what are those things? Be very specific. That's 100 points. Proportion standard deviation, they're not. No. And they're not p hat either though. So good. I'm throwing 500 points, and this is why I pause right here, because it's very hard to know how to use this. It takes a lot of practice. So 500 points, don't worry about being wrong. So with this right here, this is quantitative data. The first thing we should always ask when doing a sampling distribution question, and you'll hear this in the Kahoot, is categorical or quantitative data. Categorical. Categorical data is like, do you own a cat? Is someone from Tennessee? Do you like Taco Bell? It leads to yes, no questions, like the proportion of people who have this. Quantitative data is like, how much money do you make? How much did you pay for that? So it'll always be numbers. It'll always be numbers. Quantities are always numbers. So this says a standardized test has a mean of this. So is this quantitative or categorical? Is this quantitative or categorical? This is the first thing you should do when doing one of these questions. Is this quantitative or categorical? Which one is it? It's quantitative. Great job, Jonah, right there. So it's quantitative, which means we've narrowed it down to quantitative data. Now, because we know it's quantitative data, we go to the formula sheet and we remove from our eyes the things we don't need to see. It has nothing to do with the top portion right there. None of those things apply to the problem because that's only categorical data. So now the problem deals with this information right here. So now tell me, what is the thing in blue? What is the thing in blue? Who knows? Perfect. What is the thing in blue? So it has a mean score of this. Don't worry about being wrong. These are things we have to understand to be able to do well on the test. Because on the test, I won't be there to explain it. So we have to be able to do this ourselves and be like, okay, so mark the notation, know if it's quantitative or categorical data, and then be able to identify on the formula sheet where these things are at to find certain quantities we're going to need to solve the problem. So what is this thing right here? What is that? No, take a guess. Don't worry about being wrong. What is this thing? We've got all this down here, so we can take any sort of guess we want. What is that thing right there? What is it? Kinda. So this says the mean is this. Mu is the mean. Mu. Now, mu will be the answer to what is the expected sample mean. So when you see this mu, we usually read that as expected sample mean. So that quantity I've highlighted in blue up there is the mean, and that tells us the expected mean. If I tell you historically the average on test 2 has been a 75, what would you expect the sample of our students to get? So if I tell you historically there's been an average of 75, what would you expect the sample of our students to have as a mean? Notice how I read this. Historically, there's been a 75 average on Stat 1 tests. What would you expect the sample for our class to be? 75. And that's where you get mu y bar, which is the expected sample mean, is equal to mu. So understanding what we're saying right there is very important, that if you took a sample mean, you would expect it to be the true mean. It doesn't say it will be, it just says the expected. So now we found that quantity right there, and now we need to know the standard deviation. So what is the value in orange? What is the value in orange? Just tell me the notation for it. You were correct. No, you were correct. 144 is the mean, which is mu, and then standard deviation is 7, but what is that in notation? We've already done the mean, the first thing here. This box is completely checked off. We've done that information. So it is, and you are correct, it is SD, but it's not quite SD. What is it very specifically? 100 points? Well, it's not expected standard deviation. And we don't call it expected. And good, Catherine, I'm gonna throw you another 500 points. This is tough, and this is big practice. The standard deviation of the data, stated as a fact, is gonna be sigma. Sigma. And thank you for, just keep working through it. Sigma is the true standard deviation of the data. This is the standard deviation of the mean, the sample mean rather. That is the standard deviation of the sample mean. Mu is just interpreted as expected. This is still read as standard deviation. That's still standard deviation right there. And then it'd be just the standard deviation of the sample mean. This can be read as the mean for the sample mean, but that kind of sounds weird when you say mean for the sample mean. You can just say the expected. Like the mean is what is expected. So we're just changing it from being called mean to expected at that point. So what do you think the things in green are, where it says we have a small class with 4 students and a large class with 36? What do you think those are? What do you think those are? This is a really good question that basically does most of the chapter. Hence why we're doing it very slowly, knowing the notation. What do you think? Not sample statistics, 100 points. You're technically right. I'm gonna throw you another 500 because you're technically right. A sample statistic is what they are. They are sample sizes, which is a sample statistic. So I stand corrected. You are correct. Those are sample statistics, and a sample size is a sample statistic. So because statistics come from samples, it is a sample statistic. Very specifically, it is a sample size. So you didn't say anything wrong. They are sample statistics, and they're a sample size. They are n, the sample size. So now, guess what we're going to do is we're just going to solve these formulas. So going here and solving these formulas, where's my mouse? We got the small class and the large class. Notice how we're focusing on the theory right now. The small class, what is the expected mean for the small class? What is the expected mean for the small class? What is the expected mean for the small class? You have to look at the formulas. What is the expected mean for the small class? We're doing this in more parts than they'll have you do. We're just solving everything. What is the expected mean for the small class? 144. What's the expected mean for the large class? What is the expected mean for the large class? I'll disappear and zoom in a little bit. What is the expected mean for the large class? 144. As n increases, the mean stays the same. Notice how this has nothing to do with mean here. As n increases, the mean doesn't change, teaching the test. The standard deviation for the small class is going to be equal to the original standard deviation of 7 over square root of 4, which is going to be 7 over 2, which is going to be 3.5. The standard deviation for the large class is going to be equal to the original standard deviation of 7 over the square root of 36, which is going to be equal to 7 over 6, which is equal to 1 point, and then 1/6 is 166 repeating. So we have right there the mean and the standard deviation of the distributions. Now we go to the problem and see what they want us to do and give them the answers. So would you expect the sampling distributions and sample means to be for each organization? 144, we just said that. So the distribution for the larger, both distributions are approximately normal with a mean of 144, and that's because the underlying data is normal. So the new distributions due to the large enough n condition will be normal. Now this says from the samples, they had a mean of 151. So now from the samples, there was a mean of 151. What is the notation if I say from the samples, they had a mean of 151? So I want you to tell me in notation, if I say from the samples, they had a mean of 151. What is this in notation right here? From the samples, they had a mean of 151. It says from either organization's sample, I wish they said sample right here, they had a mean of 151 from the samples. So what would that be in notation? From the samples, they had a mean of 151. What is the notation of this? From the samples, they had a mean of 151. Write this down if you don't have it. Every time we do a notation, write it down. I don't know is a fine answer too. Remember, you can always say I don't know. It shows me you're following along. That's fine. I don't know. That's a good answer. 100 points. It is Y bar. That is Y bar. And if we go back to the formula sheet right here, you'll notice Y bar is the only thing we hadn't marked. So right there, y bar was the only thing on the formula sheet we did not mark yet. We have the mean, the standard deviation, all that stuff right there. So now we take, because we know they're saying for a y bar equals to 151, we plug in right here the formula 151 minus 144 divided by 3.5, and that is equal to 2. Then we go over here and we plug in 151 minus 144 divided by 1.166, and that might be equal to 6 or so, or 5. Let's find out. 7 divided by 1.666 equal to 4.2. I hope that one's correct. 4.2. And so those are the z-scores to tell us how unusual they are. So 2 and 4.2. All boils down to notation in this chapter. Very much notation. Where'd it go? Here we go. So they were 2 standard deviations for the small class and 4.2 for the larger class. It's more likely the smaller class will have this due to the less unusual z-score. I thought I did something wrong. It's this z-score right here. Did I calculate the standard deviation wrong? Let me go look at that standard deviation again. Something felt wrong about that as I was doing it. 7 divided by square root of 2 right there. It's because it's square root of 4. And that looks correct. And then 7 divided by 6. That's that. And there we go. What did I enter wrong? I thought it was like 6. That's what I did in my head. I said it was 6 in my head. It's a lot of steps. It's very easy to make errors. I had a calculation error there. I thought that looked wrong. Hence, when I was doing it, I was like, something seems weird about that. That was the one I was thinking that something was wrong on it. Now it says the mean score from a sample is 138. This is a different what? The mean from the sample, hint, 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 is now 138. This is testing a different what? The mean from the sample is 138. This is testing a different y bar. So now we go back to the sheet right here that we've been working on and plug in a different y bar. And let's go right there. Oh, that's the wrong sheet. That's wrong. Here we are. Going over here. And 138 is the other mean we're testing. 138 minus 144, observation minus mean over standard deviation. That's -2. So man, they were nice on that. Oh no, it's not -2. Not math. Let me enter that into the calculator. It's 6 divided by, but it's, I'll show you the full steps. I don't want anyone to be confused. I'm doing it partially in my head, and I got to remember, you can't see what's in my head. There we go. -1.71 there. Negative. There we go. And then 138 minus 144 over 1.166 equals 2. Oh. -5.15. 515. Seem right. So that's 6 below. So the smaller one is less unusual. Well done. Yeah. That's a lot of steps right there. Big question to understand, and it really boils down to notation. Like every bit of that problem boils down to not messing up your notation. So it's solving everything on this formula sheet right here. So it is a tough question, but it's a good question. These down here were just the formula repeatedly solved. So we were just going through and multiple times doing this formula right here. So this formula wanted blue. See that? This formula right here was solved repeatedly to get the z-score, which these are right here, that the z-scores to tell us how odd they are. And the smaller the z-score is, the closer it is to 0, the less odd it is. The further away it is from 0, like in the terms of negative or positive, the more odd it is. Going back to chapter 5 knowledge, that z-scores are just how many standard deviations something is away from the mean. If you look at the formula right there, it's the observed sample mean minus the true mean divided by the standard deviation. So big formula to know right there. Let's check out this one. I think it's a shorter one, which is good, but we'll put some knowledge into it. Here we are. A waiter believes the distribution of his tips has a model that is slightly skewed to the right with a mean of 9.60 and a standard deviation of 5.40. Complete parts A through C. So explain why you cannot determine the probability that a given party will tip him at least 20. That is a party. So with this, it'd be very hard to do because the distribution is not what? Don't read their answers. The distribution is not what? So it says a party, a singular party. It says we have a skewed distribution like this. A party, it's not normal. So we can't really use empirical rule. So it's not normal. So the distribution is skewed, meaning it's not symmetric. So there we go. It's not normal. That's the whole thing is, it's just not normal. Usually where the one says you can't do the normal model. So yep. Now we have 4 parties. So what we're actually talking about right here is if you were to take, and I don't know if I can do exactly 4, but if we were to go right here and do 4 parties, and I really wonder, I'm going to go over here to UTverse, start a new chat really quick, and I'm going to say this. I'm going to say, build me a shiny app in R that takes from a slightly right skewed distribution 4 observations when the button go is clicked. The parent distribution will have a mean of 9.40 and a standard deviation of 3.0. The applet will animate the observations being taken. Someone can click 100 to do 100 simulations. Both distributions will be shown and summary statistics given, including mean, standard deviation, and skewness. Okay, if this does it, I will be amazed. The distribution, I want to see if it does in the background here. The distribution of the mean as n increases will become more what? The distribution of the mean as n increases will become more what? So the distribution of the mean as n increases will become more what? You can see right here with a smaller n, a larger n, and an even larger n. The distribution of the mean will become more what? So you can go from a smaller n to a larger n to an even larger n. It'll become more what? From a smaller n to a larger n to a very large n. The distribution will become more what? 2 things technically. And I'm trying to show you here with this button. It'll become more what? 2 things. Knows in the chat. The distribution of the mean, which is what they're talking about right here. They're saying the next 4 parties will have an average tip. So that's the mean of 4 parties. Will become more normal. So can you estimate it using the normal? Great job, Rachel, right there. Yep. Let me see if this applet works here. It'll become more normal. And the problem is this is skewed. So I don't know if that's a large enough. This goes to the large enough condition right here. Because when it's skewed, we probably need about at least 25. They kind of get, hey, Blakely, good to see you there. So 4 is probably not large enough. So that's the problem, is that this is probably not large enough. There it even says it for the central limit theorem, CLT. That's what they're saying to kick in. So it's probably not large enough. Now they up it to 10, and this is where it gets iffy. And this problem, I wish it just said, maybe. Like it just say maybe, which it kind of does, but it's 25 is just a guideline. 10 might be large enough. While a sample of 10 parties may not be large enough to use the normal model, it is likely that the sample average is starting to approach a normal. The standard deviation is 1.71, and that is what it's going to be. How do we know that? Go here and do 10 square root and divide the original standard deviation of 5.40 by this, and you get that number right there. There it is. How did I know that? Well, that is the original standard deviation divided by the square root of n. This formula right here, we just plugged in the numbers, and you can see it on the calculator still. 5.4 was the original standard deviation, and we divided that by square root of n. So the original standard deviation of 5.4 divided by the square root of n gets us the new standard deviation. And I wish they just had you input that value. It just is not a good learning way to just tell you this value. Even if it's slightly skewed, this is still more normal than not. And we're going to see this really quick right here. So I'm going to see it wrote a bunch of lines of code for me. I'm going to see if this worked. Okay, let's get R up and going. Where's my R Studio? Really quick aside right here, because I might be able to simulate this. If this works, I'm going to be amazed that I was able to code something this quickly. Well, I didn't code it. I'll take credit for it though. I gave it the prompt. And so here's the code we got. I might not even have all the, I do have shiny. Good, we're good. Okay. Does it work? Does it? Let's find out. No, it's not showing it. I don't see the visualizations. Oh, we're redoing the prompt again. Redoing the prompt in the background and seeing if it works. Time for the next question, the dreaded waiter-waitress problem. So the prompt is being redone right here as we do the dreaded waiter-waitress problem. This problem boils down to knowing what? If you're still here, tell me what Leo always says. It's scary, right?
Notation,
boils down to knowing your what. I'm gonna mark the question right here. What does this problem boil down to knowing? This problem truly is just one of these problems. Notation, brother. So let's start marking that notation. Let's get it going. And great job, Jonah, right here. This is the practice we need. Batman, the hero Gotham needs, not the one it deserves. Maybe it's the hero they deserve, not the one they need. Something like that. Harvey the one? I don't know. One of them was the one they needed. They got both. Harvey Dent. Dark Knight is so good. Like, top movie ever. Don't disagree. Also Deadpool, also Spider-Verse. Okay, let's do this question right here. It says, a waitress believes that distribution of her tips has a model that is slightly skewed to the right with a mean. And so if we see slightly skewed to the right, we should think Monster Man. There he is right there, slightly skewed to the right, to the high is the Monster Man's tail. Right to the high, left to low, whatever way the Monster Man's tail goes. And the mean is this. So what is this in notation? I'm going to mark it with a color right there. What is the mean in notation? Where's that value on this data? Is it P? Is it Q? Is it N? Is it P hat? Is it STP hat? Is it mu Y bar? Is it mu Y Y hat? Is it mu P hat? Is it mu? Is it sigma? Is it N? Is it, what is it? Is it Z sub Y bar? Where is it on this screen? What is the mean is this? This is where people get stuck. You've got a lot of things to choose from. It's not P though, 100 points right there. It's not P. P is proportion, true proportion. And this is where we always have to ask when doing these questions. Are we dealing with categorical or quantitative data? So our tips, like how much money you make, categorical, like yes, no questions, or quantities, like amounts. Are tips categorical or quantitative? Are tips categorical or quantitative? Quant, yes, it's how much money did you make. So since it's how much money did you make, it's quantitative, which means when we look at the formula sheet, we remove some of the information so we don't have to worry about it. This question has nothing to do with proportions because proportions is for categorical data only. So it has nothing to do with proportions. We're only dealing with this. So what is the mean now in notation? So the mean in notation is what? We've narrowed down choices a little bit. It's mu. It's mu for mean, population mean. Great job, Rachel, right there. It's mu. And so what would she expect her tips to be? Remember, this mu now is read expected. It is still the mean, but I usually read that mu as expected sample mean. So sample Y bar. So then Y bar is the sample mean exactly. So the expected sample mean is the true mean. And great work, Rachel, right there. What is 4.5? What is 4.5? It says the standard deviation is this. What is that? So quantitative QQ, that's for regression. Good work. What is the standard deviation of 4.5? What is that in notation? Once we get all the notation marked, we can usually just fly through the problem. The hard part is knowing what to do with the information. Then you can just solve it. I might be able to guess these. Probability she'll make $600. How many tables is she doing? Oh, 10. What is 4.5? I'm trying to solve it in my head right now. Tough one to do in our heads. The z-score about... Taking one guess at this. Tell me what that 4.5 is. I get one guess at these problems. Or decimal place accuracy. Now it's gonna be smaller than that. The standard deviation, it basically kind of very close, Rachel. That right here is sigma. So the standard deviation of the sample mean means we need to take the sample size, and this will give us the standard deviation. Yep, I think we just did that one, Blakely. Yep, if you we have it, we can swing back to it, but that we've been doing them in order right here. So check it out. We can swing back to it though if you want. We just did that one though, but we can swing back to it after we complete the homework. And so does that make sense, Rachel, right here, how I have everything marked? The standard deviation is 4.5. She waits on 60 tables. That's the sample size. And then this is technically the sum of the observations of Y. So that is the sum of her tips. And then if we want to find out the sample mean, we divide it by. It's kind of like saying I have 10 pizzas and 5 people are going to eat them. So you'd have on average 2 pizzas per person. So with 10 pizzas and 5 people, person, there we go, you would get 2 pizzas on average. Like if she has to make $600 on 60 tables, she would need to average $10. Like she wants to make 600 on her 60 tables, she'll need to average $10. So that is Y bar. So Y bar equals 10 for this problem, which means we just found Y bar and we have every component of this problem now. Notice how we have Y bar. We also have mu Y bar, which is technically this also, and we can calculate the standard deviation. So the standard deviation of Y bar is equal to the original standard deviation of 4.50. Yes, we need to find the standard deviation of the sample mean. So that's how this is read, is the standard deviation of the sample mean. So this is the standard deviation of the sample mean, the variation you would see in sample means you take. So it's this chapter is so theoretical is the tough part, because you're talking about when you take sample means, a random sample mean of 25 observations is going to be somewhere on here. We'd expect it to be 11.19, but there's going to be variation. That was actually a really weird one, interestingly. The first one I got was very towards the tail of the distribution, but the means you get would come from a distribution when you take a random sample of 25 and then find their mean of these 25. They would come from a new distribution with a new standard deviation, and notice that this is the original standard deviation of 8.95. Well, 8.95 divided by square root of 25, 8.95 divided by square root of 25 is 1.79. So notice how I was able to find the new standard deviation by taking the original and dividing it by the square root of n. And that's what you're finding right here. You're not using the original standard deviation of 8.95, which your problem has a different one. You're finding the new standard deviation for a sample size of what is ever given. And that's what we're doing right here by taking 4.50 and dividing it by the square root of 60. That is the new standard deviation for a mean of 60 observations. So 60 square root. The theory of this is the tough part. So 0.5809. There it is. And so now what we do is we go to the applet. On the test, you would probably, let's find a z-score instead, because that's what the test would do. This is how the test would have you do it. You would do a z-score. So we take the sample mean of, we're just solving this formula right here. And notice we have everything marked for the problem with color coding. The sample mean was 10. The true mean is 8.8. The standard deviation is 0.5809. And thus the z-score is a little bit more than 2. Should have been close with my answer. 2.06. Yeah, it's a tough chapter. I can almost guess this one. I'm gonna do something crazy. I'm not gonna trust in myself. So close. It really wants very small decimal place accuracy. There we go. That's my guess. Let's go to the applet and look at the answer. Okay, so we're gonna go over to the applet because I have one last guess. If I'd seen that, I would have probably had a better guess because now I know the z-score. And we go over here and we can just enter in the z-score we found by going above the z-score. And the answer is 0.0194. If you notice, 2% is what I would have guessed if I had two decimals. The next decimals are the hard part, 0.0194, because we found the z-score right here, and that is the probability above the z-score of 2 point, that long one right there we entered. So this is a tougher problem right here. Enter in the z-score is one way of solving it, and that's more test relevant, but 0.0194. And that should do it. And I would have gotten it wrong, but I was very close with my 2% guess. Now, here's what we need to do to solve the last part. The best 1% of weekends, would that be on the right or the left side of the curve? The best 1% of weekends, is that on the right or the left side of the curve? The best 1% of weekends. The best 1% of weekends. Is that on the left or the right side of the curve? The best 1%. Think about her tips. Would she be on this side or this side? The best 1%. Right or left side? Which side of the curve would that be on? The best is the upper part of the curve. So we go over here and we find the value using the p-value and go in, enter in 0.01. Now make sure it's over here on the right, because you're on below, you need to enter in 0.99. You just have to make sure this line is on the right side of the curve. And I usually like to do it as 1% and do it right here to see the top 1%. We're going to take our standard deviation of 0.5809, enter it right here, 0.5809, and we're going to take the mean of 8.8, which the problem gave us. And now this is her what tip on the best weekends. So I'm going to pause for a moment here, see if anyone knows. This is her what tip on the best weekends. This is her what tip. Is that her full tip? Is that how much she makes? Well, no, it's not her best tip. Good answer. It's not her best tip. This is her, it's not her highest tips. It's the highest 1%. That's right there. Jonah, 500 points, keep answering. But this is the distribution of the what, meaning this is her what tip. This is her, think about what we're solving for. Not this one. Applet go. This is her what tip. I'm gonna close the applet. It is her mean tip. This is her mean tip. I don't know why it's doing that. This is the mean tip for her. This is the mean tip because we're solving from this because this is from the distribution of the means. So this is her mean tip because remember all the formulas we're solving are for the distribution of the mean. So if you see right here, this is the expected sample mean. This is the standard deviation of the sample mean. So this is her mean tip. So if she were to make this on average from 60 tables, how much would she make from 60 tables? If she made that much on average from 60 tables, how much did she make from 60 tables? What do we need to do with that info? She made this much on average. Kind of, sort of. Well, we're about to do this next. You can use inverse norm and normal CDF. For the test, you don't need to do it though, so you'll find z-scores. So it's okay to do, it's not bad, but visualizing it is better, and then understanding what you're doing and knowing when to find z-scores is best. I've had people make great grades with a basic calculator and bad grades with a TI. Usually having a TI helps though. Like, it just doesn't mean you'll do well if you have a TI. It's not like, I get a TI and do great. It's good, TIs are great, but they can just supplement what you're doing. Well, kind of, so imagine this. So this value right here is her average tip from 60 tables. If I told you you weighted on 2 tables and averaged $10 on those tables, how much money did you make? You weighted on 2 tables and you averaged $10 on those tables. Your average was $10. How much money did you make on the 2 tables? 20 bucks. So what if you weighted on 60 tables and this is your average? What do we do right here? Good to see you, Neandra, right there. If you had 60 tables and this is what you averaged, what would you do? So do the same work you just did, because a lot of times when the numbers are decimals or bigger, we have problems because we know what to do. But then, well, so it's not quite, very close. Yep, we'll go back and check it out. So you weighted on 60 tables. That is correct, Rachel. It is 600-ish. It's like 600, 607.5 or so. 607.5, which might be a close enough guess. 607.5, about. Nope. Now we got to go solve it. So what do we need to do? Oh, nice job, Jonah. So we have to take, that probably looks correct right there. I did the wrong, I know what I did wrong. There we go. I also did something else wrong. I did 600 tables because that's why we always have a guess in our head. We're just multiplying by the number of tables. There's the answer right there. We go back to our problem. So you multiply the average tip by the number of tables, and that will get you the answer right there. Multiply the average tip by the number of tables, and you're good to go. So there we go. Good stuff. Made a mistake on the 5, actually. Next question right here. Good question. I do that one many different ways. It's just people learn differently. So check out, if that one didn't make sense, check out maybe another version where I worked it out differently-ish. It's just, sometimes it clicks for someone when I teach a certain way. It's a tough question. Which of the following is not a condition to check to estimate the mean of a population? Ooh, I need to show Terry this. Well, that is true. That'd be right. Yeah, I think Terry, I think that would be true. Because we can't model it with the normal. Yeah, this is correct. It's not to calculate the sample mean. Yeah, that's very, very exact. So which of these is not a condition to check? Does anyone know? Which of these is not a condition to check? Great job, Blakely. Oh man, I've already given out so many points. People are already at the massive bonus. Give out too many points. Give out some more right here. Hope it'll show up. You can do it. Which of these is not a condition to check when doing the sampling distribution of the sample mean? This goes back to the notes. So from chapter 13 forward, we always have the first 2 conditions are the same. Exactly. The first condition is the data was randomly collected. So this is a condition we check. The next condition is do not sample more than 10%, which is the less than 10% condition. And then we put those what's in the chat. For 100 points, we put those what's in the chat. You can give bonus to the top point getter. What do you put in the chat when we get to the third condition? As we always go, when doing our conditions, you're watching this, don't think about just getting this question right. Think about learning the material. From chapter 13 forward, it's always condition 1. Randomly collect your data. From chapter 13 forward, the remainder of the class, it's always random, then less than 10%, and then you put what in the chat? Who knows? Why not 1,000 points? If someone can say it. I won't give it unless someone says it, though. What do you need to put in the chat? You're in class yesterday, you know it. Put those what in the chat, because you have to slow your mind down. You have to what? What do you have to do? What do you need to do when you get to the third condition? Say it here in a second, but I want to see if you remember it. We always do this. Well, and that's why the thing, though, we always pause. We always pause. So you always pause right here. So you always pause and you stop. The reason is because the third condition for the remainder of the class will depend on the data we are doing. So these are the things. Don't think about just getting a grade on MyPearson. Think about knowing the material. If you look down here at this video that I have for test 3, you can really see that we have to pause because the third condition will depend on what we're doing. Notice how every condition is the same for proportions, means, two means, and chi-squared. It's always random and 10%. And then you have success failure for categorical data, nearly normal, which is a condition we'll talk about more on test 3. And then for chi-squared, it'll be count data. I think I put that in that box, expected cell count, and then count data down there. So the conditions right here is where they change. Does that make sense? So how many conditions will be the same from chapter 13 forward? How many conditions will always be the same? From chapter 13 forward, how many conditions will, every time we do conditions, will always be the same? From sampling distribution, sample proportion forward to confidence intervals to hypothesis tests, they'll always be the same first two conditions, random 10%. And then you have to think, what kind of data am I working with? The problem is we learn success failure first, and everyone's always like, success failure. And I'm like, wait, that's just the first condition we learned when we started learning these new sets of conditions, depending on what we're doing. Success failure is only for categorical data. Right there, you can see I marked a C above it. Chi-squared has categorical data also, but does expected cell count for the chi-squared cells. More on that later. That's the last chapter of the class. So we always pause when we get to this. So when you hear the sampling distribution of the sample mean, which of these is not a condition for it? Which of these is not a condition for it? Which of these is not a condition for it? A, B, C, or D? The sampling distribution for the sample mean. Which of these is not a condition for it? A, B, C, or D? Which of these is not a condition for it? A, B, C, or D? See if you can answer this. This is huge. There's a question just like this on the test. Once again, teaching to the test. It is A. Because success failure, and don't worry, Jonah, 500 points again, don't worry, practice here. Success failure deals with what kind of data? Success failure deals with what kind of data? What kind of data uses the success failure condition? Success failure uses what kind of data? What kind of data is used for the success failure condition? Proportions, great job, Amy. Yep. And so proportions would do success failure, where quantitative data would do the large enough n condition, which you see right here, where here we have large enough n. I actually did this in purple this time. So large enough n is for quantitative. Now, they kind of say that with this. This is pretty much the large enough n. I wish they described it differently, but we would not do success failure for it. It's very clearly that. So good question, checking conditions. Success failure is not used for quantitative data. We would use the large enough n, which means as the sample size increases, the distribution of the mean will become more unimodal symmetric, which they allude to in D. They just don't say large enough n, which I wish they did. We will say that on the test, though. We make it a little more clear to how we teach on the test, which is good. They kind of go for the vague, you know, like how you might hear someone else talk about it. So you have to understand what the concept means. Where on the test, we try to be as exact as possible. Here's question 6 right here. According to the central limit theorem, what are the theoretical mean and theoretical standard deviation? So we're going to mark notation to begin with. And Amy, good to see you here. So what is the formula for the new mean? What would be the mean for this distribution? What would be the mean for this distribution? Do you see it on this sheet right here? Because it says we are trying to do a sampling distribution of sample means of different sample sizes. And we want to know what the mean and the standard deviation are. It had boxes for the mean and the standard deviation. So how would we find the mean? How would we find the mean? How would we know it? Well, it says the mean for the distribution of the sample mean, or the expected sample mean, is equal to what? That's what we want to find. We want to find that quantity, and we want to find this quantity. So we've actually figured out a lot already on this sheet. Well, that's what we want to know. We want to know the purple and the orange quantity. That's what's being displayed in the box right here. This is the purple and this is the orange for the different sample sizes. So how do we find mu y bar? What is the expected sample mean? What would that be? What would be the expected sample mean? The expected sample mean is just equal to the what? The expected sample mean. Yeah, that's it. It's just this right here. And that is the quantity of this right there. So that is the true mean, which is what we would expect. So I've circled it for what it is. It is this quantity right here. Mu is that. And then mu lets you know what the expected sample mean is. And then the standard deviation, I'll do different color highlighting. The standard deviation is this. There it is right there. And then we have to get the new standard deviation. So what's really great is what happens to the mean as the sample size increases. This is another teaching the test moment. What happens to the mean as the sample size increases? What happens to the mean as the sample size increases? You can see it here in the answers, and you can see it in the formula. As sample size increases, what happens to the mean? It stays the same. It doesn't do anything. The sample size is not in this formula. It's in the standard deviation formula. Yeah, we just did that earlier, Skylar. Check out, I think it's question number 3. We just did waiter waitress question. Check out in the video. We could swing back to it. I'm gonna try to do the formula sheet after this, but check out earlier. I think it's question 3. Here, I'll hit save. It might actually have in the description now the links. So you might. Here it is. There's the links. I just added the links to the video, but there you go, right there. It should be in the video-ish. Let me know if not, but there it is right there, the questions. So with this right here, the standard deviation is what we want to solve next. So what do you think is going to happen to the standard deviation as n increases? As n increases, the standard deviation will do what? As n increases, the standard deviation will do what? It gets smaller, exactly. And that's one of the 2 things of the central limit theorem. The central limit theorem states that the distribution of the mean or proportion will get more normal and tighter as the standard deviation, as the sample size increases, the standard deviation will get smaller. All I'm doing is changing the number at the bottom. Notice that I've highlighted all the sample sizes up here, and we will just kind of permeate through all the sample sizes, changing from 30 to 50 to 100 to 200, and divide by the square root of those. So there's the formulas on the screen on the previous Word document, and we take the square root of 30, and we find that first, copy it, and 18.996.59 divided by that, and there's the first answer. Next answer right here, 2 decimal places. Next answer is 50 square root. I love the mathy chapters because if you do the math right, you don't get it wrong. With that said, I make math errors. So here we go. We enter in this one, and then we delete down and make sure it's rounded. It is. And then we do 100. And what's really great is we just move the decimal, because dividing by 10, square root of 100, is just a decimal move. So that should be the answer right here. And then 200, is it 14.14? The square root of 200? 14.14. There we go. I had to memorize stuff like that as a kid. Like, what's the square root of... Oh, you know what's so interesting? I just realized something. That's not right. Let me redo that. There we go. I just realized something neat. Pretty sure square root of 2 is 1.414. You can ask your phone too. You can always ask your phone. What is 18,996.59 divided by the square root of 200?
It's approximately 1,343.2617.
There we go. That works right there. Ask your phone, type it into Google, Wolfram Alpha. Lots of ways of doing that right there. Does that mean the square root of 20? Why does it work? Oh, I know why. Because when you factor it, that's interesting. Because 200 factored can be the square root of 100 and the square root of 2. And then you can multiply those square roots. That's interesting. Didn't know that. I don't know, just figuring out math things right now and realizing them that they work that way. So there's the answers right there. We should be right. We've done it. How close are the theoretical values? Well, this is a simulation which shows us reality, and you can kind of check your answers here. They won't be exact, but this is a simulation which is not meant to be perfect. It's just doing simulations. What I mean by this is, if I go over here and do the simulation right here, and I were to clear this and do a bunch of simulations, theoretically, this value right here should be 8.95 divided by square root of 25, and it is this 1.79, but the simulation right now has this 1.94. Theoretically, 11.19 should be 11.9 down, 11.19 down here, but it's right now 11.29. This is also the law of large numbers, that if I continue doing the simulation, then the values will approach the values here. So that's the law of large numbers. Yeah, and it's tough. I think saying it to your calculator is good, but try to punch it in, because on the test you won't be able to talk to your phone. The theoretical values are reasonably close, and the other values are reasonably close. So because simulations model reality. Let's try to see if our ChatGPT applet works now. It actually looks more filled out. Just a real quick interjection of the applet we made to see if it works. And the answer is still not doing it. Oh, wait. Ooh. Ooh, it's actually doing it. I don't like the way it's displaying it, though. It's a different random sample of 100 each time. Oh, and then it put the 4 up here. That's a sample of 4. Interesting. So you can see the mean of 4 is further away, and the skewness goes down. Huh. Yeah, it's kind of doing it. It didn't animate it well enough, but that's better. I could work with that and fix up that code and get something I wanted. So we made a little central, I just made a little central limit theorem applet right there. It's not nearly as good as I'd like it to be, but I could improve that. I could prompt it more to make some changes, but that's getting closer. Okay, the last homework question right here. And then I'm going to do the formula sheet because I want to put that out there in a video. For this question right here, this is the sampling distribution right here, and it is what skewed? This is the sampling distribution right here, and it is what skewed? This distribution right here is the sampling distribution, and it is what skewed? Right skewed. That is right to the high, left to the low, whatever way the monster man's tail goes. So this is right skewed right here, not left skewed. Right skewed. And with this right here, the simulations do support, they'll always support what the central limit theorem says, because as the sample size increases, you'll notice that the distribution becomes more normal and tighter. By tighter, look, this goes from 0 to 24,000, and this only goes from, I know that's not quite 0, but 0 to 17, 18,000. So it's becoming tighter because there's less variation as we increase the sample size. And these are means of sample size 200, and these are means of sample size 30 from this parent population right here. Now, because this is super duper skewed, it didn't become normal enough. The peak of the histogram, which is the mean, does not change. It stays about the same. The shape becomes more normal, and the variability, known as the standard deviation, gets smaller. It decreases. And these all go to the formulas right here that we've been looking at that say the mean for the distribution of the mean is equal to the mean. The mean stays the same as sample size increases. The standard deviation gets smaller because we're dividing by the factor of the square root of n, so it'll get smaller, i.e. less variability. It's important to understand when reading this, when it says the variability, which is standard deviation, decreases, and the peak, which is basically saying the mean right there. When it says the peak, that's the mean staying the same. It becoming more normal is the central limit theorem, which we've reviewed a lot today. And there you can see the data was skewed and becomes more normal. When you have a large enough n, it'll be normal enough. And the problem with this is 30 is not always enough. Sometimes when data is very skewed, you need a much larger sample, and that's where we get to the large enough n. Sometimes you need even 1,000 if it's super duper skewed. Super duper. So the more skewed it is, the larger n needs to be. So you can't say 30 is always enough. So because since the distribution of means becomes less skewed, no, it doesn't hold. Since it remains skewed, it doesn't hold. 30 does not always work. Sometimes you need very, very large samples. Tougher quiz and tougher homework, but it takes practice and knowing the notation, which is how we're going to end today. I want to put this in a video format. I want to do the full formula sheet for the test. I was going to do this to start, but we've done the full homework now. Now we're going to do the full formula sheet. Is anyone here wants to see everything mentioned on the formula sheet? And let me mark this. This will be the full formula sheet because I think this will help people for the test. And it's test prep time. Okay, if you are watching this right now, please go and print the formula sheet. Go and print it out, and then have note cards beside you. Have a note card beside you. With your note card, start writing down things I have, take notes. Just hearing me saying these things will not be enough help. You need to either say them out loud, write them down, come up with your own examples. You want to practice it along with me. Just hearing me saying it won't be enough. So print the formula sheet and have your notes ready. Let's start reviewing. So with this, let's take the first thing, say goodbye to Monster Man, and go to regression. Regression is chapters 7 and 8. So let's make a note right here. Regression notation, which is chapter 7 and 8. 8 is regression, 7 is regression, and 8 is regression wisdom. And this is the part of the formula sheet that goes over the regression notes. So you notice right here we have y hat. Y hat stands for, and I guess I'll write it, y hat, I'll do it as notation right here, stands for the predicted or expected sometimes, the predicted from the regression equation. The predicted from the regression equation. So predicted value of y. And what does this mean? Well, it means if we have an equation, we would predict that an observation has this value. Take, for example, we look at somebody studying for a test, and we have their hours studied, and we have their grade. We could use previous data to draw a linear model, and the linear model is going to be what makes the predictions. So that is where the y hats come from. They come from the linear model, which is this equation. Y hat basically is that because it's built from the equation. Like if you solve that, you get y hat. So these two things right here are one and the same. It's not that y hat is b0 or y hat is b1 or y hat is x. Y is the mathematical solving of that equation. Y hat is, it is the linear model's predictions. And when you make a prediction using a particular x, you get the value of y hat. So now what is the value of y, which you see right here? Y is the value of an observation. It is the observed. It's what we see. So y, lowercase y technically, is observed value. So the y's are right here. It's what you see. It's what somebody made on the test. Notice if we trace this over, we get an actual value. This can also be called the actual. And right here, the line would give a predicted for a particular x. So that is the y hat where it hits the y-axis right there. So you notice we're already talking in terms of actual and predicted. And down here, a value of an x is simply where you are making a prediction. So the x would be someone's hours in this instance. So we'll highlight this in orange right here. That is just whatever the value of the x variable is. So it's the predictor variable. We'll call it that, or the explanatory. And this is the response variable. Observed value of response variable. So the y is the response, the thing we'll talk about. Think I'm responding to someone saying, well, here's what I think your grade will be. That would be the y hat. And here's what you actually made for your grade. That is going to be the observed value of y. Your hours might explain, studying, might predict your grade on the test. We could also have a model that doesn't have a strong relationship right here, but the X explains why something happens. So we would plug in the values of X into a formula. You'd get a formula like predicted grade is equal to 40 plus 5 times hours. And with this, you simply plug in for hours, something like 6 hours of studying, or let's go, not be 6, let's go into 10 hours of studying, sure. And this is cumulative, because that's a lot of studying. So if you did 10 hours of studying, apparently according to this model, we just plug in right here, 10 times 5 equals to 50 plus 40, you are predicted to make a 90. So you might have been predicted to make a 90, so that would be your prediction. The model predicts you'll make a 90, but you actually make a 100. So that's what you actually score. Notice we're kind of just pretending this person made a 100 right here, and they were predicted to make a 90 according to the data in the model where the X value was equal to 10 hours of study right there. So with this information provided, we can actually go through and find what is called a residual. The residual is going to be the actual minus the predicted. So the predicted comes from the model, and the actual is the observed value of Y. This is where you'll usually hear me say residual wrap, where residual equals actual minus predicted. Residual in notation is technically E, so a little tricky right there to remember residual is E. And it's really just how far away are these two values. You see in the the yellow-orange right there, that is how far they are away, and they have a distance of 10, as in the actual was 10 higher than the predicted. And we can solve this, that 10 is equal to, we have minus the 90, and they actually made a 100. So look at the color coding right here, how we have the actual score they had on the test, the predicted score they had, and they scored 10 points higher. So if the residual is positive, they scored higher than predicted. This is the positive zone where you're above the line. This is the negative zone where you're below the line. So positive residuals mean you are higher than you're predicted to be, and negative residuals mean you're lower than you're predicted to be. The only other quantities we haven't mentioned right here are B0 and B1. And B0, if you've been following along right here, B0 is equal to the estimate of the intercept. B1 is equal to the estimate of the slope. Now you need to know the interpretations for these. These are on the test. We would say when x is equal to 0, we expect y to equal B0 on average. Next, we have the interpretation of the slope, and the slope interpretation is for each 1 unit increase in x, we expect y to increase/decrease by B1 on average. So here we are with each of these for you. And we can go back to our formula right here, and let's highlight these. For the intercept is this, and the value of x is the hours someone studied, and the y is the grade. X highlighted everywhere. I'm just going to highlight everything I can. And the y is somebody's grade. And there's the y. And B0 is highlighted everywhere. No, we need one more B0 highlighted. And this is where people have trouble on the test when we ask you to write it out. A lot of trouble writing it out. I don't want to use the same colorish. Go here for yellow. There we go. And the slope is positive, so we're going to use increase. Okay, read this along with me, or try to, because this is the practice we need. When somebody's hours of study are 0, we expect their grade to equal 40 on average. This is logical because someone who doesn't study would probably not make a good grade. It's a logical value, meaning it has a logical interpretation. Things without logical interpretations would be when somebody's weight is equal to 0, you can't weigh 0. We'd expect their height to be this. Or when somebody studies 0 hours, we expect them to make a -50. Well, you can't make a negative grade. If when you say the interpretation out loud, it doesn't make sense, it's illogical. So you have to say it, just be like, when someone's height is 0, what? No, that's illogical. Then interpret it and mention that it's illogical. The next one down here for the slope is for each 1 unit increase in somebody's hours studied, we expect their grade to increase because the coefficient's positive by 5 points on average. This is the slope right there. Let's highlight that. The slope value of B1, the estimate of the coefficient of the slope is B1, and it is 5 for the example problem we gave. And the last thing to interpret, which is not here, is the R squared. R squared is blank percent of the variation in Y is explained by the variation in X. So when you have your X and your Y, put them in here with the right context. There's X, there's Y. Come up this problem, we'd have to give a theoretical R squared, where R squared is equal to 88. You always do it times 100 if it's given as a decimal. So it would be 88% of the variation in somebody's grade is explained by the variation in somebody's hours studied. 88% of the variation in someone's grade is explained by the variation in hours studied. And this is a full note right here, chapter 7 and 8. Let's do the next one and do another note sheet. I'm going to mark all these individually, and I might go over, probably will go over on office hours. I'm just going to rock and roll through these. Next, we have probability. Okay, probability. There we go. Probability. Let me copy this right here, write it down. Jordan, Elizabeth, good to see you. We've done the waiter waitress one. It's marked in the video here. I'm going to finish off with this. It should be at about the 45-minute marks. If you scroll back through the video, let me know if you have questions. I'm going to finish the formula sheet right here to mark it in the video for everybody. But let me know if you have questions or I can find it for you. We did the waiter waitress one. We did it last time too, I think. But check out this video. It is in this video right now. Check it out. So good questions. Elizabeth, good to see you there. So this is chapter 12, probability. And if you're doing this right now with us, grab your notebook, grab your note cards. Remember, just watching me do it is not going to be enough. You want to have your note cards beside you. You want to write these things down. You want to come up with practice problems like we just did for chapter 7 and 8. So what's the first thing say? It's actually the first rule of probability. It says the probability of the set of all outcomes. And this is the sample space. The set of all things that could be awesome. See you in office hours, Jonah. So this is the sample space. The sample space is everything that could occur. Like a 6-sided dice has 1, 2, 3, 4, 5, 6. That's the sample space right there. A coin has a sample space of heads and tails. And so if you look at everything in the sample space, the probability will be 1. If we draw a table to label it, we could say the event and the probability of the event. So we have the event tails and the event heads. The probability of tails is 50%, and the probability of heads is 50%, thus leading to the probability of the sample space is equal to 1. When you add up everything in the sample space, something must occur right there. So that's what that's saying. The sample space is everything that could occur. The probability of something in the sample space occurring is 100%. Next, you have rule number, actually that was technically rule number 2 for probability. Rule number 1 is all probabilities are contained between 0 and 1. You can't have a probability that's negative or over 1. The next rule is that sample space adds up to 1, which we just saw. And rule number 3 is that the complement is 1 minus something. So this is known right here as the complement. E. So the complement is to say not the event. And we just do 1 minus to find the complement. There's also the fact that if you take the probability of not A and the probability, or the probability of A, they would equal up to 1. And notice how you could just bring this over to the other side and do the math. right there that you have. You would just algebra it over. So the complement and something else are a sample space. So if you write here, like, my parents say either I'm going to get a bunny or not get a bunny, and you say, of course we're going to get a bunny. So the probability of bunny is equal to 0.90. The probability of not bunny is now equal to 0.10. If you notice, that is a valid sample space. It's everything that can occur. Tonight, you're either getting a bunny or not getting a bunny, and one of those things must occur. This is the same thing right here, just worded differently. It's just saying the probability of A can be found by doing not A, or 1 minus not A. And so we also have the same sort of idea right here with this. Next, we have the addition rule. Very clearly notice a few things here, that the addition rule uses the word or. It's doing addition. So this is the addition rule. Rule number 4, and it uses the rule or the condition that they must be mutually exclusive. So these are the words, the mathematics, and also the rule, and it's here on the formula sheet. Mutually exclusive is the same thing as saying disjoint. Same thing as saying disjoint. These mean the same thing. They are synonyms right there to say something is mutually exclusive or they are disjoint. If something is disjoint, you have A occurring and B occurring, and they never occur at the same time. So this is disjoint. They exclude each other mutually. If you have A and B and it looks like a Venn diagram where there's an overlap, this is not disjoint. So the best way to test if something's disjoint is you literally say the following. Try writing this down in note cards. Bo, good to see you there. We say, I just found out A occurred. Like, I know it's a record high today in Knoxville of 110 degrees. Is it snowing? Well, you'd say, well, obviously not. So then that would fall into the category of disjoint. It can't be 110 degrees and snowing. Now, be careful. If I say it's 10 degrees outside today, that doesn't mean it is snowing. It just means there are instances where it's 10 degrees and it could snow. Because you're saying, could it be 10 degrees? Yes. Could it snow? Yes. They could both occur. Can it be 110 degrees? Yeah, sure, it's happened. Can it snow? No. When it is 110 degrees, there is no instances or possibility in the world that exists where it's 110 degrees and snowing. So that would be disjoint, 110 degrees and snowing, but not disjoint is when we have instances of 10 degrees and instances of snow. They can both occur at the same time, so they're not disjoint. So then let's say Knoxville has crazy weather. Knoxville has crazy weather, and the probability of snow is equal to 5% of the time during crazy weather. It's a very high probability. Probability of 100 plus weather is 1% of the time. So what percent of the time would you expect it to be 100 degrees or snowing? And in Knoxville, that would equal to the addition of these. What's the probability of 100 degrees or snowing? We're not saying like it is this and this happening at the same time. We're saying like, well, in Knoxville, how often is it 100 degrees or does it snow? So you just add together the two probabilities as shown by the equation up here. So that is how we check disjoint to see if we can add things by simply adding together the two probabilities. They can't have overlap, which means they occur at the same time, i.e. they are disjoint, they don't have overlap. The next thing you see is the multiplication rule. And the multiplication rule is the fifth rule. And we use different words for it. We use and we multiply, and they need to be independent. Independent means if you know one thing, it tells you nothing about the other. If you know I didn't drink coffee this morning, do you think my wife drank coffee? She might have. Actually, it's funny, on Monday morning, I didn't drink coffee. Does that mean my wife didn't drink coffee? She'd actually be less likely, but she did drink coffee. I didn't drink coffee because I had a dentist appointment, just regular cleaning, good stuff right there. But knowing Brian didn't drink coffee might lead you to believe maybe something's wrong with their coffee maker. Maybe they ran out of coffee. Because when I don't drink coffee, it's probably because we didn't make coffee. If I see coffee in the morning, I drink it. And so maybe my wife was running out the door and I was running out the door, so neither of us had time to make coffee. So independent does not mean you know the answer to the other thing. It just means we know Brian drank coffee. His wife's probably more likely to drink coffee. They are dependent on each other drinking coffee to some degree. The probabilities change. So think about a coin flip. I know that this coin just flipped tails. is the next coin flip independent? Does knowing what we flipped right here on this coin tell you anything? So if you feel in the chat maybe, does knowing what we just flipped tell you anything about the next coin flip? Like I know it's tails, I can see it. Does that tell me anything what's gonna happen next on the next coin flip? No, it's completely independent. The next coin flip is completely independent of the previous coin flip because knowing what we just flipped, I know what we just flipped, that tells me nothing about the next flip. Notice how we check these. Independent means you have to say, I know what just happened. Like Brian drank coffee. Does that tell me anything about his wife drinking coffee? Yeah, it kind of does because they kind of, one of them drinks coffee, the other one drinks. But knowing a coin flip would be independent because I know what I just flipped tells me nothing about the next coin flip. So if we ask, what is the probability of getting 4 heads in a row? We would say, what's the probability of getting heads and heads and heads and heads, which is going to be 0.5 times 0.5 times 0.5 times 0.5 right there. Notice we're saying and when we're saying that right there. So that would be 0.0625, I believe. We can double check our work here. Probability of getting 4 heads in a row. There it is. Now, what's the probability we have at least 1 tails? So this is where I ask you to write a sentence. So if you've watched my videos on doing these problems, if I say, what's the probability of at least 1 tails? You could go crazy right here because a really long way to solve this, which I'm going to try to do super quick, is to write out all the sample space. If you write out the full sample space of everything that could occur, you would have here heads, 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 tails, or we should do the permutations the right way. Tails, heads, 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 tails, heads, 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 tails, heads, 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 head, tails, tails, heads, heads, tails, heads, tails, heads, tails, heads, heads, tails, heads, tails, tails, heads, heads, tails, heads, tails, heads, heads, tails, tails, heads, oops, yeah, it's fine. We're on to the next. Heads, tails, heads, heads, whoops, I went the wrong way. Tails, tails, heads, tails, tails, heads, tails, head, heads. And then we're almost done. Man, this is the long way of doing it. There's everything that could occur. You know what we just found? We just found this. This has a probability of 0.0625. You will either get all heads or you will have at least 1 tails. This, everything here, is the sample space of everything that could occur. Since we know it's the sample space adds up to 1. So you will either have, and we can write it over here on the first page, you'll have either at least 1 tails or all heads. Notice how that's the addition rule because you can't get all heads or at least 1 tails at the same time. They're disjoint. You're either going to have at least 1 tails or you're going to have all heads. It is the sample space that everything that could occur, and the sample space is equal to 1, which we already said in the previous rule. I love these questions because they basically use everything. Because to find out the probability of all heads, you have to go and find the multiplication rule right here. The addition rule comes into play because these are disjoint, and the probability of at least 1 tails is simply going to be algebraing this over to the other side. This chapter takes a lot of practice. It's very mathy, but these problems right here really, and they would be minus now, really test your ability to understand how everything comes together. So 1 minus this right here is going to be the probability of at least 1 tails right there. So at least 1 tails is equal to this because you're either going to get all heads or at least 1 tails. Those are disjoint things, and that makes a sample space of everything that could occur. Sample space has a probability of 1, so you just subtract from 1 that amount. And if you take the time to draw it out, it might make more sense. I hope seeing this for someone's like, oh, wait a minute, that's the sample space. The sample space has a probability of 1 because I wrote all the probability of getting 4 heads or 3 heads or 2 heads or 1 heads or 4 tails right there. You can see the combinations. I didn't find all the individual probabilities. I only needed to know 1 because I know everything in here would add to 1, but I can just subtract from that the other probability. Take a look at this chapter, but that's the notation on here. Knowing the formula sheet is going to be key because you also have, and I can't state this enough, the conditions right here. The addition rule uses mutually exclusive disjoint, same thing. The multiplication rule uses independent. The formula sheet, which you get to print off, is a cheat sheet. Now we're on to the last part of the formula sheet right here. If you're in the chat, say hey. We're going to do the last part of the formula sheet. Okay, let's do the formula sheet. You are watching this video. Start when I start right here. I clip these out. If you are watching these videos, I cannot state it enough that you need to print this off. You already heard me say it multiple times. Follow along, write the notes, come up with your own examples to remember how to do these things. Just watching me do it is probably not enough because it's hard to remember these things unless we put it in our own words and we try to write it out. So try to follow along right here, practice writing these out as we talk about chapter 13/14 right here. We'll add that to the notes. This is chapter 13/14 on doing the sampling distribution of the sample proportion or the sample mean. Now, a big problem people have is when they do these chapters, they usually remember the proportions better than the means because it's the first thing we learn. So whenever you do a chapter 13 or 14 problem, the first thing you need to ask is cat or quant. And by cat or quant, we're talking about the variable type. Is it categorical or quantitative? And right here, if we say it's categorical, like do you own a cat, then we would choose proportions. Categorical data leads to proportions. Quantitative data leads to means. So quant right there, means. And so notice right here, that categorical data is like, do you own a cat? Yes, no. Proportion data, categorical is proportions. Quantitative data is like, how much money do you make? $2. Or how fast did you run that race? 18 minutes. Or how tall are you? 73 inches, sure. So these would be quantitative data points versus do you own a cat? Are you married? What street do you live on? Things like that are going to be categorical because they put people into groups. So with this right here, the first question you need to do before doing any problem is find out if it's categorical or quantitative data. And once you find that out, you will only look at the portion of the sheet that deals with the equations you are using. So here we are, we have a question like this. It states, we know from the UT registrar that 70% of students are in state. Hanging it up. We sample. What's it mad about? Is it a dash? We sample 200 students and want to know the mean and standard deviation for the sampling distribution. Find out if it is odd that 150 students were from state by giving a score. Okay. We have a saying here, and it goes... Notation, brother. So we always mark our notation to start, and I could have told you a little bit more because questions will state this. This question is, are you in state, which is categorical. So because we're doing, are you in state, that's a yes, no question, and people usually get confused on these because they see concepts like, and we'll highlight it here, they start to see what is the mean right here, and they're like, aha, we're doing the mean. But the truth of this is, we're basically saying the mean is the expected. And so when you hear mean of the sampling distribution, change this mu right here to be read as expected. And then you're saying, what is the expected sample proportion, which is the center or the mean of the distribution. So I would expect the sample proportion to be the true proportion. And that's how this is right here, the expected sample proportion. So p hat is equal to sample proportion. P hat is always equal to x over n. X is the amount of successes. N is the sample size. Lowercase n. Capital N, not used right now, is used for population size, or normally distributed if done differently. If you see it like capital N equals this, that's the population of UT. Not used in this problem, but could be used to check conditions. But that's when it's stated as a fact, not n with parameters. With this right here, we can go ahead and actually solve this because we actually have this information in the problem. We have the amount of successes given as 150, and that is the amount of successes from a sample size, the sample size of 200 right here. And you'll wonder, like, well, how would we know this? It kind of goes to things we normally take for granted. Like if I say 5 of your friends out of 10 want ice cream, what percent of your friends want ice cream? Well, you'd say 50%. If I said 8 of your friends out of 100 own a Ferrari, what percent of your friends own a Ferrari? You would say 8%. You're just doing 8 friends out of 100. The amount of successes is just the times we see something over the number of observations. So we usually understand what sample proportion means. It's just the proportion we see based on the sample size and how many successes there are. So we've actually gone and found a quantity right here, the sample proportion. We'll highlight it in, let's do a yellow. Has already been found for this problem right here. That is the sample proportion, which is p hat. Now the true proportion, we have so many colors, is p. The true proportion right there is p, which is used right here. This is stated as a fact and often given to you in a problem, and the true proportion is how we know what we expect to see. So think about this. If it is true that 90% of students, or 70% of students are in state, I would expect, if I took a sample, to see that. So I expect in my sample, the expected sample proportion is equal to 70%. So if I took a sample, I'd expect to see that. And that's why when we draw this out, we go to the very center of the curve and put right here mu p hat. And so since mu p hat is equal to 0.70, we go right here to the center and we put 0.70 at the center of the curve. But every curve needs a mean and also needs a standard deviation. The standard deviation is the variability. So to find the standard deviation on the curve, we have to go in here and we have to find out other quantities. So we have P and we also need Q. So where we play the P and the Q game, because P and Q are complements. If you watch the other video, if P is equal to 0.7, then Q is its complement equal to 0.3. Notice how these two together add up to 1. So you can just do Q equals 1 minus P or vice versa. That's how you find it. They just must add up to 1. So this quantity right here is going to be 0.7, and the other quantity is going to be 0.3, found by 1 minus P. We also know what n is from this problem. N is 150. And look, we can now solve for the standard deviation. So the standard deviation, which is the variation in the sampling distribution, is equal to 0.7 times 0.3 over the square root, or the whole thing square rooted of, oh my, someone's got to catch that error on me. 150 is x. Someone might have watched that. Sorry about that if you're watching this video in the future. I was like, that's not the numbers I was using. Very easy to make errors. And that's not the mean. I've been going for a long video right here. There we go. We're color coding everything. I hopefully will make no errors, but they can happen. Please put them in the comments if you see an error. There's the color coding associated with it right there. Lots of things are on the screen right now, like the sample sizes, the true proportion, the complement of the true proportion, and we can find the standard deviation right here. So the value of the standard deviation, let's go ahead and solve that, is going to be P times Q over n square root. And so P times Q over n square root. About 2%? 3%. 3.2. Carry all decimals on the test. There it is right there. And now we can do the final formula right here, because notice in the final formula, we can take what we saw in our sample, subtract it from the truth, and take the standard deviation, which is right here. I totally have the orange pen selected, and just see likely, and we can divide by that. So now we're going to take the quantity down here, which will be 0.032, and we're going to take the quantities up top, which is p hat of 0.75 given by the problem, minus the truth. We're going to color code those so people can look at the sheet when I pause at the end. There's that. The sample proportion was this, and this will find the z-score. And the z-score for this is going to be about 1.6 or so. And we take and subtract, there's the camera, and there we go, 1.54, which means if you go here and start marking the standard deviations, you'll notice that 0.75 would be right about here-ish. And because this is 0.73 and this is 0.76, if you go through and mark it, the points are like the 1.3, there's the smoky level. Yep, and this is where p hat is right here in this problem, 0.75. So that is where we are at in the distribution. We are at a z-score of 1.54. If you notice right here, that's 1 and 0.54 standard deviations above the mean in terms of z-scores where the observation landed. So the last one right here, we got one more problem right here. I'll mark this as chapter 13. And this is the test 2 prep. Great job, Blakely. I'm hoping people use these videos to understand the formula sheet, which can be complicated to look at. Chapter 14 right here is going to be the last part of this. We'll just grab this right here. Once again, I'm going to say it for the 10th time. Make sure to print this out and write down the notation. So we have to know cat or quant. And because we're doing chapter 14 right here, it's always going to be quantitative if you're doing chapter 14. But you have to know you're doing chapter 14 to know you're doing that when you're doing the sampling distribution of the sample mean. So this would deal with things like money, height, weight, GPA. So all those things right here are quantitative, which means we are dealing with the mean of this. Now be careful, there's mean elsewhere. There's a lot of mean stuff around here. But just hearing mean is not enough. You need to hear things like the sampling distribution of the sample mean. So you want to hear sampling distribution of the sample mean. And that's what this means right here. If you connect the words, we're saying the sampling distribution of the sample mean. And that's what this is right there. You notice the color coding, and that is quantitative. So a problem for this one with the notation is going to be something like UT knows the GPA of students is a 3.5. You go with a standard deviation. Now, a lot of people do this problem really quickly and they say, that's not odd at all. If someone can solve this problem in seconds and tell me if it's odd or not odd, I'll be impressed. A lot of people, if you're already solving it and saying, that's not odd, you probably use chapter 5 on this instead of chapter 14, which is how this is solved. You say, well, why would we not use chapter 5? Well, we're not asking, is 3.8 odd? We're asking if the sample mean of 3.8 from 100 students is odd. So knowing the notation is key right here, because this value right here is a sample mean. Y bar is equal to the sample mean. Y bar is sample mean. We'll write that over here on the side. Y bar equals sample mean. And a sample mean would have an associated sample size. And the sample size for this is 100 right there. Notice we're already marking a lot of the notation. Next, we have what the UT registrar says the true mean is. So the true mean is equal to this, same color, can't do that. The true mean is equal to this. Running out of colors. That is the true mean. And so mu is true mean or population mean. As in, like, we know this is the truth for all the data. So mu is true mean, the population parameter. And then sigma is true standard deviation of the population. And sigma, you can go find it in the problem. Nice light green. It's going to be right here. That is sigma. From this, we can find the new standard deviation. The new standard deviation for the distribution of the mean, which is this, the standard deviation of the distribution of the mean, is going to be equal to, standard deviation for the distribution of the mean is equal to 0.3 divided by square root of 100. So it is equal to 0.03 because it's divided by 10. And now you might see where this is going. We're not going to use that standard deviation. Samantha, good to see you there. This standard deviation right here is the quantity used to look at the difference. So we've got a lot of stuff because is this odd is basically asking what is the z-score. So we need to find the z-score to figure out if something is odd because z-scores standardize differences for us. And now we already have the mean. So let's go ahead and mark that right here. We've actually done everything. And we can draw out the distribution. And we know that the mean for the distribution of the mean, I did this one really quickly. The mean for the distribution of the mean, which is the expected sample mean, the expected sample mean is equal to 3.5, and the standard deviation is equal to 0.03. Remember, this is the new standard deviation, not the original. So as you go up, you'll notice we're getting nowhere near the other value, the 3.8. And it'd be way off the curve. It's completely, it's over there somewhere. We don't even see the value. It's way off the curve. So now we actually have to use the formula of taking the sample mean minus the mean of the distribution over the standard deviation to find out that it's actually a z-score of 10. We'll highlight everything in here. We have the sample mean given by the problem from the 100 students. We have the mean of the data, which the registrar gave us as a true value. We have the new standard deviation found by taking the original standard deviation and dividing by the square root of n. And then we have the z-score for is this odd. The z-score for this is this odd, and this is super odd because it has a z-score of 10. So understand that this chapter really boils down to notation right here. This is the mean, and this is the standard deviation right here. So that is really computer. Oh, that is standard deviation of y bar, and this is the mean for y bar. There we go. So really good stuff. A lot of stuff going on right here. A lot to understand and to know. Knowing the formula sheet is key. Practice these. Know what each of these things mean in notation. Ask questions. We still have like 5 days for the test. Until then, bye for now, everyone. Bye. We've almost got these new intros ready. We're almost there.
This has been going for like 20 hours. This ends now.